Yeah, so we're discussing how to synthesize a voltage controlled voltage source. And the discussion that we had in the previous class was there are four basic types of control sources, right? So we have uh, VCCS, vcvs, CCCS, and CCVS. And we tried to characterize them with respect to the expected input and output impedances. And if we form a table, this is what we should get. If I see write R in and R out, again, for VCCS, right, voltage control current source, what should be the expected R in or desired R in? It should be infinity, 0, infinite, right? So ideally it should be infinite, but in reality it should be Rin should be much greater than Rs, whatever is the source resistance that is driving this control source, right? Because infinity is often, I mean, in principle you cannot achieve. Similarly, for vcvs, the control terminal is again, you are expected to, it is expected that a vcvs will have a control terminal which is a voltage control, which means the input impedance is supposed to be infinite. Again, not possible. So it has to be much greater than Rs. When we look at the output side for voltage control current source, what is expected at the output side? What is the impedance, expected impedance at the output side of a current source? It's a current source. So what is the expected output impedance of a current source? Ideally, 0 or infinite? Infinite, right? Because you ultimately, what is the model? The model is this, right? So you have some control terminal and you have, I mean, if you, all of these four can be modeled as a two-port network, right? You have two terminals which are controlling the input and two terminals which are controlling the output. So you let's say you have a input here and you have an output here. So these terminals and these terminals are the input and the output ports. Now, any two-port, any linear two-port network can be modeled in one of those in a generic form, right? The one that we had discussed long time back. This will be the input impedance, then you will have something like this, then you'll have something like this, and the output impedance and so on. So in case of a unilateral system, right? When I say unilateral, which means the signal only flows from the input to the output, not from output to the input, which is expected. All of these control sources are unilateral, right? You have the controlling terminal is this terminal, and whatever the effect you are seeing is on this terminal. So the reverse is not true. So which means since it's a unilateral control source, so this guy y12 should be 0. So the only thing that we are left with are input impedance, output impedance, and some and this y21 parameter, right? So now just because we sketched this in terms of the way we have sketched this, it looks like this is a current source, y21 V1. It need not necessarily be a current source. We saw that in yesterday's class. There has to be a certain relationship that has to be satisfied to first to understand whether the stuff inside the box is a current source or a voltage source. Now, with regards to the output side, what is the expected relationship between, let's say this is R out and RL, so that this stuff inside the box behaves like a current source? This is where you give me the answer. Question not clear? Yeah, right. So when the stuff inside the box needs to be should behave like a current source, then obviously the expectation is entire current flows into the RL, right? Not inside its own impedance, right? Not inside its own internal impedance, which means ideally I would want R out to be infinity, but in principle it's not possible. In reality, it's not possible. So the next best thing is R out should be much greater than R. Okay. And similarly, if the stuff inside the box has to behave like a voltage source, then essentially I want this voltage to that develops should be independent of RL, right? If that voltage develops, that is expected to develop is independent of RL, which essentially means that all the current should flow into its internal source, internal resistance, right? So then the current times its internal resistance will be the voltage, and you keep on changing the RL, it will not get affected. In other words, your expected R out is 0, ideally, but in principle, the one that we should aim for is R out should be much lesser than RL. Right? When it's I mean, this is nothing holy, right? This is nothing out of the ordinary. This is all we know. I'm just recasting the same thing that we know in terms of the expected impedances. Okay. Similarly, for current control, current source, the control terminal is input terminal is expected to be a current control, which essentially means that if we divert our attention to the input side, so what is the maximum possible current that you could have extracted from the in or the source is V in by RS. This is the maximum possible current that we could have extracted under the condition that this R in was going to 0, right? If R in is infinity, then there is no current. If there is no current, there is no point in building a current controlled source. Right? A current control source by definition means that there has to be a current that has to be coming in, and I'll take some action based on that. If there is no current that is coming in, there is no action to be taken. So if you are designing a current control source, essentially you have to design the input impedance in such a way that you invite current in. So how can you invite current in? Under the condition that R in is 0, right? Or R in is much lesser than RS. Okay. So expected R in will be 0, or R in is much lesser than RS. Similarly, I mean, the next one is also current control. So R in is much lesser than RS. Again, if we look at the output side, this is current control current source. So R out has to be infinity, or R out much greater than RL. And this guy becomes the other way around. Okay. Okay, fine. So, so this is what we discussed at length in yesterday's lecture, and then we said that let's start building one. VCCS we already know. A simple transistor itself is a VCCS that satisfies our condition that input impedance is infinite, because looking into the gate you get infinite impedance. Output impedance is also the way we have modeled the transistor. Incremental is infinite, because if we look into the drain of a transistor, the Y22 is 0. Right, the transistor is essentially a current source, because the output because the current, the IDS is not dependent on VDS, right? Since you can keep on changing VDS as long as the transistor is in saturation, the IDS isn't changing, which means it's a current source. So by default, if a transistor, a MOSFET is a VCCS. So next thing that we are trying to see if we can design a vcvs using a transistor. And we took the strategy that let's argue our way through it. And the argument that we were giving was, okay, we understand we have an input V in, and there is a resistance RL. So so the argument that we were giving is whatever we have to put inside this box should be such that again, I mean, we were not trying any voltage controlled voltage source. We were trying a voltage controlled voltage source with a gain of unity, right? With a gain of 1. So so the argument that we were giving was, if we observe the difference between this input terminal, let's say I call it VI. If we observe the difference between this input terminal and the output terminal, and we take some action in such a way that that difference goes to 0, right? That difference goes to 0, then it is then whatever block we will be manufacturing should behave like a voltage source, right? Should behave like a voltage control voltage source. So with respect, I mean, in the following that argument, what we essentially said that, okay, VI is, we cannot control, VI is given to us, which essentially means that we have to take some corrective action on V naught. We have to change V naught in such a way that it tracks VI, right? So if we have to change V naught in such a way that it tracks VI, then naturally the question becomes, how do we do it? So the way we do it is, we observe the difference, that is, we observe VI minus V naught, and we have to change V naught, right? Because V naught is in our control, VI is not in our control. So we observe V naught and change V naught in such a way that the difference goes to 0. Now, how do we do that? So the argument is, if V naught drops, right? If V naught reduces, I should be pushing in more current into V naught. And if V naught increases, I should be pulling out current out of V naught, right? So that's the whole argument. Now, when I am saying I'm pushing in or pulling out, this has to be done automatically. And what should that automatic thing be tracking? It should be tracking the error. It should be tracking this error, which is VI minus V naught. If VI minus V naught increases, I should be pushing in more current into RL and vice versa, right? So if that is the case, we need a device which can do this for us automatically, right? We need a device which can sense the difference and push in current. And a transistor is a device which senses the difference and pushes in current, correct? So if we just place a transistor here in the direction that I show here, where VI goes to the gate and V naught goes to the source, then this current will be GM VI minus V naught. So in principle, looks like if we connect the transistor or its incremental model in this format, then if somehow V naught tends to drop, right? If somehow V naught tends to drop because maybe RL has changed for whatever reason, then the transistor action is trying to compensate for the drop in voltage, right? So whether it will be good enough voltage source, whether it will be able to succeed in doing so, that's a part of analysis that we'll do. But this is what, yes. Because we are trying to get into an incremental voltage control voltage source. Right? So everything is about incremental. We are not looking at the quiescent, or we are not looking at total. Okay, so even when we are building amplifiers, it was an incremental gain, right? So again, it's an incremental source. Okay, so now the thing that where we ended yesterday's class was trying to evaluate whether this contraption satisfies the condition of the impedances, right? So then we said that what is the impedance looking inside this? That is what is effectively the Y22 of this or 1 over Y22, or what is the effective R out of this contraption looking from the perspective of RL, right? You take the RL out, put a phase voltage source, and see what is the impedance. And we saw that this impedance is 1 over GM, right? So this impedance is 1 over GM. So as per the arguments that we have laid out, as long as we can make 1 over GM to be what, much larger or much smaller than RL for voltage source? Much smaller there. As long as we can make 1 over GM much smaller than RL, if we can make this much smaller than RL, then this should behave like a voltage source, right? It should behave like a voltage control voltage source. Control part is easy because input impedance is infinite, that is getting taken care. The output side, we have to ensure that. Now, this is what this is where we stop. So next thing what we should do, what I would like to do is do a brute force analysis of V naught over VI, and then see if this condition is satisfied, what happens, right? So can you do that? Find out V naught over VI. Yeah, so let's do a KCL at V naught, and you will get V naught over VI to be is equal to GMRL by 1 plus GMRL, right? So you see that this condition is equivalent to saying GMRL is much greater than 1. Right? If you satisfy GMRL to be much greater than 1, then this is almost equal to 1 as long as GMRL much greater than 1. Right? So as a designer, as long as you can design, if you know the range of RL, if RL is likely to change, if you know the range of RL, then all you have to ensure is that you prepare your transistor in such a way that you bias your transistor in such a way that its own GM, its own quiescent GM, right? It becomes is such that GM times RL is much greater than, or 1 over GM is much lesser than RL. Then you should be able to design a voltage controlled voltage source with a gain of unity, incremental gain of unity. Okay. Okay, fine. Any questions till now? Yeah, we'll do that. We'll also do that. Not in today's class, in a couple of lectures from now. So by the way, this is a useful expression to remember, to by heart, right? Because this is a configuration, this will repeatedly keep on coming. There will be some configurations which we'll use multiple times. This is one of them. So this expression is something, if you by heart, it will be easier for future analysis. Yes. Okay, so his question is, what is the importance of error voltage? So the importance of error voltage it will become more clear as the course progresses, but for today's lecture, the way you should think about is, so what is the purpose of whatever of this voltage source? It's voltage control voltage source is trying to change V naught, and in a way it is trying to track VI. Right? If VI changes by a certain amount, V naught should also change by the equal amount. Right? So now VI is not in our control. VI is an input that is coming from somewhere else. So what we are trying to do, we are trying to ensure that we have to design the circuit in such a way V naught keeps pace with VI. Right? If VI increases, V naught increases, and vice versa. So now, how do we do that without looking at VI? We cannot do that. Right? We have to have a tracking mechanism of looking at VI. So how do we track? We always, even in our mental models, let's say when you were riding a bike or a cycle or something, you are supposed to go on a straight path. Don't try this, but imagine that you close your eyes and you go. So almost invariably, you are going to veer off course. So what is our eyes doing? Our eyes is giving us a feedback that this is the trajectory I should go. But in reality, I am going in this trajectory. If there is a difference, I am closing in the difference and taking a corrective action through the steering. Right. So, okay. So I'll answer that question also, but let me complete the thought process. Right. So if I use that same example that I was talking about riding a cycle, so this is equivalent to that you see that I want V naught to be tracking VI. If I don't have any tracking mechanism, if I don't have any error detecting mechanism, then V naught can go in its own direction. I don't know where. And VI can go in its own direction. So there has to be a coupling, right? There has to be a way I should track the movement of V naught with respect to VI. So one of the easiest way to track is to see the difference, right? If the difference goes to 0, then perfect tracking. If the difference doesn't go to 0, there is no tracking, right? So now let's see in this case. So by the way, that is the reason of tracking the error. Okay. Now in this case, let's see what is the error. When everything is settled, what is the error? So in this case, VE will be VI minus V naught, which is equal to what? VI by 1 plus GMRL. Right? So if GMRL is much greater than 1, if GMRL, for example, tends to infinity, then the error goes to 0. Right? So that is the importance of that error, right? You are trying to minimize the error. I'm not sure whether I answered your question, but again, if not, can you repeat your query?
Because does that if V naught upon VI is always nearly equal to 1,
It's not necessarily always equal to 1, right?
We set a GM, like if GMRL is more than 1, so it's always going to be equal to 1. So I don't need to worry about the V.
Okay, you are talking about this particular architecture or general architecture?
This one.
Yeah, so in this particular architecture, you have to set GMRL to be equal to much greater than 1. Then you don't have to worry. But how do you know that this is the requirement? Right? That requirement comes from the architecture. And the architecture comes from the thought. Yes.
We don't have just concept. That means we don't have already formed here.
Yes. Okay, so if you want the voltage of the voltage to come a gain of 1, then you need to make it. Other way of thinking about it is, let's say I don't want a gain of 1, maybe 0.5 or something. Then can I set this in such a way that this is now equal to 0.5? But the key thing to note here is that it's not about that ratio. It's about the independence with respect to order. Right? I want a voltage source to be independent with respect to order. Right? So it's not, because if it's a ratio, I can use a common source amplifier and still set the GM in such a way that GM is equal to 1 over RL. That GM by RL becomes, GM times RL becomes 1. Right? But then I don't know, RL can go in different directions in the gain changes. Right? So voltage source should be able to retain its properties even when the load changes. Right? So that's why we need to impose this condition. But very good question. Does that answer? Okay, fine. Okay, fine. So this is our incremental model. So now I have to replace this incremental model with actual transistors and put biases and with whatever biasing strategies that we have, right? So now help me do it. So firstly, GM is a transistor. I can close my eyes and put a transistor. Okay, so using an NMOS, you can also do using a PMOS, but let's do an NMOS. So here, this is the gate, this is the source, right? GM VI minus V0. It's supposed to be GM VGS. So VI has to be going to the gate. So your VI has to appear here. Okay. And V0 we should be taking here. Fine. And you have an RL. And you have a VS. So now the question is, if I connect simply everything just like a small signal model, it's not going to work, right? Because the transistor has to be set up to give a to set up to accept some quiescent current so that I get the GM and so on, right? So let's do the biasing first, and then we'll put the incremental. Then we'll put VS and RL wherever it is supposed to be. At least we know that in the from the incremental sense, incrementally the VS should VI should come here, and RL should be connected between V0 and ground. Okay, so what do you think? What will be the best biasing strategy in this case? We know using current sources and so on. So how should I go about biasing this? So let's start with the input side. How would you like to bias the gate? There are only 1 or 2 of them we know, right? So tell me, just pick one. Use a battery. Okay. So where do you want to use a battery? Can you speak up a bit? Right, but where do I need to connect the battery? Okay, at the gate, right? So you can connect a battery here. Okay, so the value of the battery will decide later. Let me call it VGQ. What should I do with the source? Source I can tie to the RL. Okay, so source I tie to the RL. Other side of the RL is grounded. What about the drain? VDD essentially, right? Okay, fine. So, so now, I mean, at the input side, I know, right? I mean, if I don't want to use a floating battery, I can use coupling capacitor, R1, R2, all those things I can do. So I'm not concentrating on the input side, right? So I assume that we know how to bias that. So let's concentrate on the output side. So now, one possible issue with this type of biasing at the output side when you connect RL is it's not necessary that RL will be a floating RL with both terminals available to you, right? RL might be an input, might be a modeled input impedance of a previous stage, of the next stage, right? So it's not necessary that you might get to connect RL in this way. Okay. Another issue is that even if you get to connect RL in this way, it's not necessary that RL will remain constant. RL can vary. If RL varies, then the quiescent current will also vary. So essentially, your GM will not remain constant, right? So this becomes an issue. So yeah, so this type of connection is often not possible. So if let's assume that RL is something which you cannot connect directly, right? I can capacitively couple, assuming C to be infinity. So then how do I bias this transistor? Okay, so let me repeat. So what I am saying is that often RL is not a physical resistor that is available to you. That is quite common that it's a modeled resistor, it's the input impedance of a next stage or something. So it's not as if you can pass the bias current through RL, right? Another problem is that RL itself can vary. If RL varies, then the quiescent current to the transistor might vary. So you don't want to connect the RL directly to the source and use the RL to both set up the quiescent and also act as the load, right? So we would like to ideally like to decouple RL from the setting of the quiescent. Yeah, right. So we can connect a resistor. Yeah, exactly. We can connect a resistor here. Yes. So this is one definitely a good strategy. So this can be, let me call this R, maybe R naught, and connect this, right? So then this R naught, which is in our control, can sit inside the chip or inside your box and help in setting up the biases, right? And this RL can help us. The coupling capacitor C2, assuming that C2 has been sized to be large enough, can help us couple the input to, couple the transistor to the RL. Okay. So now the incremental model of this, right? The incremental model of this is now, so input is as is Vi. This is shorted. Capacitor is shorted. This is RL, but you have another additional RL. Right? On board with this? Okay, so now you see that this is not exactly what it was earlier. So we have in the incremental model also, we have an R naught. Right? So there will be, the effect of this R naught becomes, if you need this R naught, then you have the problem of the gain dropping, because instead of GM times RL by 1 plus GM RL, it becomes GM times RL parallel R naught by 1 plus GM RL parallel R naught. So if you have to then ensure that this works, you have to ensure that this physical resistance R naught has to be much greater than RL, right? So what is the issue if do you foresee an issue in the quiescent picture if this R naught becomes very large? Yeah, the source voltage has to increase you have to ensure that the source, the source voltage increases, and when source voltage increases, in order to keep the transistor on, the gate voltage also has to increase, right? So you can only do it to some extent before you run out of room to increase, right? So even though this strategy works well, it's not, it has some limited usage, because if if R naught requirement becomes very large, it becomes a problem. Okay, so now let's say we cannot do this. Let's say you can use a current source. So do you have any additional idea? Yeah, right. So I can replace R naught with a current source, right? I can simply replace R naught with a current source. So this goes off, right? So so you see that this architecture you have seen already, right? This one, the way I naught is setting up the bias is that auto biasing mechanism, right? You apply a current source directly at the source of the of your transistor, and the source automatically adjusts itself, right? Okay. Any questions? Okay. The issue with the previous approach will also work, but there are certain limitations, and the limitation was this. So if I use this, then you see you have to make R naught too much greater than RL. That is one piece, right? So in the Poisson picture, all the incremental current is flowing into R naught, right? So between this voltage, if you make R naught too much greater than RL, that voltage is likely to increase. This total voltage is not. Which essentially means that in order to keep the transistor on, you have to increase this VCQ, right? So you can only do it so much because you will run out of ratio after VCQ, right? Because the transistor will go out of linear if VCQ goes one threshold voltage above, right? So under certain, if you see that R naught is such that that's not happening, fine, go ahead. But if you see that R naught has this issue, that R naught requirement becomes so high that ES and VG requirement goes above VPD, then you cannot do it, right? But given that we can use current sources, the current source is a easier alternative. Okay. Okay. Fine. So this type of architecture, there is a name to it. It is often called a common drain architecture, right? This is called a So again, common means grounded in the incremental domain. Here you see the drain is incrementally grounded. In other way, the terminology common came because we take differences between terminals, right? So whatever is the common bit, whatever is not changing between the gate, drain, and source, we call it that common, that thing. So all you don't have to bother about those terminologies. All you in your mind, common means grounded. Which terminal is grounded? That is the common, right? In this case, drain is incrementally grounded, so it's common drain, right? So when somebody says use a common drain architecture, essentially what one means is this. There is another topology that is another terminology that is used. It is called a source follower architecture also. It is source follower because it should make sense, because incrementally V naught is following Vi. The source voltage is following the gate voltage, right? So ideally it should be called a gate follower, but I don't know why the name stuck, but it's stuck. It's called a source follower. There is also another terminology that is used. It's called a voltage buffer, which should be the most obvious thing to realize. It's a voltage buffer because it's acting as a block that you can put between an input and an output in such a way that even if the output impedance changes, the voltage at the input side is buffered to the output, right? Buffered means essentially replicating whatever you have at one side to other side, regardless of any change. So this is also called a voltage buffer. Or a voltage follower. depends on whoever is talking. These terms are used interchangeably. Okay, fine. Any questions till now? Okay. So if there are no questions, let's investigate this particular architecture in a slight in a different perspective. So let's say I use the same. So I'm not drawing the incremental model, but when I'm in the next part of the discussion, I'll assume that we are talking about incremental model, even though I have drawn a transistor, right? So again, what is the impedance looking in incrementally into the source? 1 over GM. What is the incremental impedance looking into the drain? If you're not comfortable, sketch the small signal model and tell me what is the incremental impedance looking into the drain. So in the incremental sense, so what are you? So source is grounded, right? So I am talking about a pristine transistor, right? So nothing connected to the source. Input side, what you are going to do? Okay, so let's assume the resistor is also connected. Then we can connect the resistor also. Let's do this. So again, the input is grounded. And what are you looking at? We are looking at putting a test voltage source here, right? We're trying to figure out the drain impedance. Looking into drain. So this is GM times 0 minus Vx, right? So if you do a KCL at this node, what are you going to get? Vs to be 0. So which essentially means that this doesn't exist. So this current is 0, which means you have infinite impedance, right? So this should not be a surprise, right? Because ultimately a transistor is a current source, right? When I'm looking at the drain terminal, the VDS doesn't change the voltage, doesn't change the current, I'm sorry, right? So which means the impedance has to be infinite. Otherwise it would have changed the current, right? Okay, so another way of thinking about it is that if Y22 is 0 of a transistor, Y22, that the way we have modeled it, the Y22 of a transistor is 0, which means that changing anything at the output should not change the current, right? The only way that current is getting changed is when input VGS is getting changed. Okay, fine. So impedance is infinity here. Cool. So now in a transistor, there are two places I can apply inputs and two places I can take the outputs, right? There essentially I can apply input at gate and I can apply the input at the source because that affects the current. Similarly, I can take the output from the drain and I can take the output from the source, right? So now given that we know all these input output resistance requirements for control sources, can you comment on if this is the input terminal, and let's say this is the input terminal and this is the output terminal of some contraption, then what will this contraption behave like among the control sources that we are aware of? Assume GM to be very high. So assume GM to be infinity. It should behave like a current control current source, right? Because looks like the input impedance can go to 0 and output impedance is infinite, right? So if I look at that table, then looks like current control current source is the best fit, correct? So we see that what can we do to use this? How do we bias this transistor so that we have a current control current source, right? So when we say we are planning to use this transistor as a current control current source, which essentially means that I'm expecting the input to have a current input, right? I expect all the current to flow into the transistor. So let's say I have a current input. Again, I'm sketching it with respect to the current input, but it need not necessarily be the case. So let's say this is I in, this is Rs of the current source, and I have to connect it to the source of the transistor. So how should I go about doing it? Again, I don't want to directly connect, right? With directly connection has those issues, right? If Rs changes, then biasing changes, and so on. I want to capacitively couple. So set up the biasing separately and then capacitively couple. So how do I go about setting up the bias? At the gate side, what should I do? Constant voltage. Again, we know multiple ways of doing that, so I am not bothering. So on source side, capacitor, and then yes. So I have a capacitor, but what I'm asking is, how should I bias this? We can bias it the same way we have been doing till now. I naught, and this couple goes here. And on the drain side, I can, let's say I have a load, right? So I have to erase this part. So I have a load. Again, I don't want to directly connect, so I can capacitively couple the load. But how should I connect? What should I do to the drain? Will this work? Taking into account effect of biasing. Where will this quiescent current flow if I connect it like this? It won't, right? I mean, ultimately everything has to flow. It will flow into the capacitor, but your transistor will not remain in saturation, right? Because there is nobody who is setting the voltage of the drain separately. So we need to ensure that the drain voltage is set up separately. So if I say that I'll just connect it to VDD, do you think it's going to work? It's in saturation, fine. But will it act like a current source? So again, so when I say that it is supposed to work like a current source, which essentially means that whatever incremental current that flows out. So now note that this is the output terminal, right? This is the out. So if I sketch this, this is the input terminal V1. This is the output terminal V2, where V1 in this case is this one, because input is getting connected here. And V2 is here. V2 is this, right? So will the incremental current that emerges out of this, will the incremental current that emerges out of this contraption flow into RL, or will it flow into VDD? It will flow into VDD, right? In incremental model, VDD is short, right? So all the current, all the I in that flows into it will end up into VDD. It will not go into RL. So if we want the current to be diverted into RL, then what should we do? Yeah, we put another resistance, RD, and we ensure that RD is much greater than RL, right? But again, you see there is an issue, right? I mean, if you cannot have very large values of resistances. If you have very large values of resistances, you have a problem, right? So as it turns out, in this case, if you, I mean, in most of these architectures, you have to live with either putting a current source on the top, that is on the drain side, or in the source side. You cannot put two independent current sources on the drain and the source. Then you end up having those issues of having to satisfy the conditions of two current sources. So you need to have only one independent source. So either you live with this, putting this I0 on the top and somehow bias and put a resistance at the source, or you put a resistance at the source and put a RD at the top. So eventually you are getting stuck with the voltage drop, but I mean, at least say this is better than nothing. Okay, so this type of architecture is also, there is another name for this. Can you guess the name? Common gate architecture, right? Simple. So this is called a common gate. Or a current buffer. It's a current buffer because the input impedance that you see here is 1 over GM. And as long as you can make, this is a current buffer, as long as you can ensure that 1 over GM is much lesser than RS. Right? It is only then all the incremental current will flow into the transistor and not into its own RS. Okay? Okay, fine. We'll stop here. Thank you.